Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're still in the realm of thermodynamics. We're talking about pure substance analysis and how to grab properties out of the property tables. But here we start to introduce a little bit of the first law. Okay, so a step up from the two previous videos. So this is a problem from UNSW, and the problem statement reads: a 0.5 meter cube rigid tank contains saturated steam at 300 kilopascals. Heat is transferred until the pressure reaches 100 kilopascals. A. Show the process on a PV diagram. B. Determine the final temperature, the final steam quality, and the heat transferred. So what's happening is we have 0.5 meters cubed of a rigid tank, so the volume is not changing there, with saturated steam inside, and that's super helpful to know, right? This means that we already know, it's not a mixture, it's not saturated liquid, it's not compressed, it's not superheated, it is saturated steam. So if I want to find everything I need to find about the first state, all I need to do is go to my pressure table at 300 kilopascals and grab all the properties for saturated steam, all right? That's for the first state. Heat is transferred until the pressure reaches 100 kilopascals. So note what's happening. We're going from 300 kilopascals to 100 kilopascals without changing the volume. How can that happen? Well, that can only happen if heat is actually leaving my system, right? So heat must be leaving my system. I'm decreasing my pressure, right? If this pressure on the second state here were increasing, right? So let's say 301, 350, 400, then I would assume that heat is going into my system. But because it's decreasing, I assume it's going out. I don't need to know this right now. This is just my assumption. We can check and be sure as we're doing the math around this problem, okay? So what we need to do is show the process on a PV diagram. So that stands for pressure and specific volume, right? So let me do a semi-straight line here. This is a pressure line P, and the specific volume is going to go here. And I believe we're going from 300. This pressure is in kilopascals, right? And I think we're going from 300 to 100. That's what's said, right? But then the volume, I believe, because it's a rigid tank, so the volume's not changing, there's no mass entering or leaving, then the specific volume needs to be the same, right? Just as a reminder, specific volume is just a volume divided by the mass. Since the mass is not changing, the volume's not changing, so therefore the specific volume cannot change as well. So really what is happening here is that we're going from state 1 to state 2 down a straight line, okay? Now, to be able to finish this diagram, I need to know what is the specific volume, so that I can put in here, and then I can finish off my PV diagram, right? So this is the only thing I'm missing to be able to finish part A. Part B, we are to determine the final temperature. That's going to be super simple, right? Because if it's 300 and saturated, oh no, that's the initial temperature, sorry. The final temperature, we first need to find out what's happening with this guy here. We know it won't be saturated steam anymore because it's losing energy. So it can be a mixture, or it can be saturated liquid, or it can be a compressed fluid. We need to check. Okay. So let's go down to the property table. What I'm going to look for here, the first thing I'm going to look for is what is specific volume for the gas. Because if I have that, I can complete my part A and put it on the PV diagram, okay? The other thing I can do is start looking for the 100 kilopascal and seeing what is the properties there, okay? If we think about it, this is state number 1. This is state number 2. What we know about state number 1? Well, we know it's saturated vapor and 300 kilopascals. Perfect. We can grab all the properties we wish for. On this second state, we know it's 100 kilopascals, but we need an extra piece of information to be able to solve it, right? And that piece of information is precisely the one that we got out of the PV diagram, which is the specific volume is not changing. So therefore, whatever the specific volume on the first one is, will be the same on the second one. Okay, so what we can say here is that specific volume 1 equals specific volume 2. So therefore, let's go and find out what is this specific volume. Let's go down to the tables. And again, I have both tables here. I have one from Rogers and one from UNIS. And what I'm going to do is I'm going to use Rogers just because UNSW likes using Rogers. And I'm looking for pressure table for steam. Pressure table for steam. So this is it. Okay, I'm looking for 300 Pascal. So that's going to be 3 bar. And 3 bar will be right here. V bar will be right here. Okay, and here I'm looking for, again, specific volume for the gas, specific volume for the saturated steam, okay, which is this column here, which ends up being this guy here. Okay, so that is the value that I need to put on my PV diagram. That's also the value for state number 2. Okay, so 0.6057. Let me go ahead and copy this because I can use this to finish off my diagram up here somewhere. Here. Okay. Oops. Oh, there you go. Okay, so this is now complete. All right, with this out of the way, what I need to do now is check what kind of state I'm in on state 2. And to do that, what I'm going to do is, okay, now I know what is specific volume 2, right? Because it has to be the same, 0.6057. So if that's the case, I need to check whether at 100 kilopascals, right, at 100 kilopascals, whether the how can I say this? The limits of the saturated liquid and the vapor are how they relate to this number here. If this is greater, if V2 is greater than the fluid, which indicates superheated, and then we know that cannot be the case. If it's in between, right, the liquid and the vapor, which means that it's a mixture, or if it's V2 is smaller than VF, which indicates a compressed fluid. That's what we need to find out. We kind of eliminate this already by means of, there's another option which is the same, right? Which would be a compressed liquid, like this, by just knowing that the pressure is decreasing, but nonetheless, let's keep our options open. And if I were to do this on this other table here, exactly the same process, right? They are supposed to be the same table. There's only very slight variations. One can argue that this one that I'm using now is a bit more precise because it's been updated more recently. Okay, so here we can see the value is not identical, but pretty much identical, right? Okay, and if you want to use this table, what we need to do now is, okay, we're going to go to 100, right? We're going to go to 100 kilopascals right here, 100 kilopascals, and I want to know between these guys here, right? This is F, this is G. This is for the gas, this is for the liquid. What is, where does the 0.6057 fall? Is it smaller than this? Yes, it is, right? Is it greater than this? Yes, it is. So it falls in the middle, right? It falls in the middle. And because it falls in the middle, we can be sure this is a mixture. Okay? And because it's a mixture and fall in the middle, then we can grab a lot of different things. First thing we can note is that if it is a mixture, then we can be sure the temperature is 99.61, which is one of the questions, right? One of the things it's asking us is what is the temperature of the final state. So 99.61 is the answer. Okay. What if I wanted, how could I do this on this other table, on Rogers tables? Well, we would do kind of the same thing. We would go to the pressure table. We would go to 1 bar. Where's 1 bar? 1 bar is right here. Okay. We would note this value here, which is 1.69, which again is greater than the 0.6, what was it, 0.6, I forget, 0.6057. So therefore, all good. Now we need to go to another table to check for the liquid one, and that's why I don't like this one that much. It takes you longer. Okay, so this is the one we're looking for now. Same thing, I need to look for 1 bar. 1 bar is here, approximately 1 bar, and there you go. It's there's 10 to the minus 2 here. That's tricky too. So it's 0.001044. Okay, so again, this is smaller than the 0.6057. So therefore, in this table too, I can conclude that this is a mixture, right? And once again, I can go here and conclude that the temperature of state 2 is, where's our highlighted section? 3 bar, 1 bar is 99.6, just like before. Okay, so we can go ahead and say, where's our question? Here we are. What is the PV diagram is done. We've done that. What is the final temperature? Final temperature is 99.6 0.61 degrees Celsius.